Hello, and welcome to the House of Law. Tonight, we begin with something you may have seen many times. A chart, a table, boxed and numbered, pasted on classroom walls and tucked into textbooks. It seems quiet, unassuming, but within it lies a deeper order of things. A map in plain sight. We are going to explore the periodic table, but not in the way it's usually taught. Not as a list of facts to memorize or a catalogue of chemicals to sort. Tonight, we'll begin to see it differently. Imagine it not as a tool of science alone, but as a soft melody in the rhythm of the universe, a quiet fingerprint drawn into the fabric of matter itself. Every element on that chart, every symbol and number, tells a piece of a greater story. A song of symmetry. In this series, we'll follow that quiet melody back to where it began. We'll trace the gentle steps of early thinkers, the quiet curiosity that shaped one of humanity's most curious visions of order. This is a journey into the calm center, where logic whispers and patterns sleep. If you enjoy this kind of restful storytelling, I'd truly appreciate it if you chose to like, subscribe, and share the House of Law with others who long for a peaceful mind. Now, let your eyes grow heavy. Let your thoughts drift inward, and come with me to a time when there was no table, no map, no key, just a world mysterious and still. Let us begin. Long before modern chemistry, before lab coats, glass beakers, and named elements, the world was simpler and more silent. For centuries, people believed that everything was made of four ancient ingredients: earth, air, fire, and water. They saw nature through feeling and form, not numbers. A running stream sparkled like water must, rising sunlight warmed like fire must, the scent of rain told them the air was near, and when they turned the soil, even the earth seemed to breathe. It wasn't science, not quite, but something quieter, intuitive, soft, something close to poetry. That harmony held for a very long time, until small observations began to chip away at it. Some things didn't quite fit. Some materials behaved in ways ancient ideas could not explain, and out of the slow change came the idea that matter might be more than just earth and air and fire and water. There might be something underneath it all. Tiny pieces, too small to see, building blocks hidden in the world's design. Seeds of form, unadorning but essential. Atoms. For a while, this was only theory. A thought still wrapped in shadows. But step by step, mind by mind, the vision cleared. By the 18th and 19th centuries, explorers of the elements were hard at work, gathering, separating, weighing, identifying strange and shining materials, naming them slowly and placing them one by one in a growing collection. Their world was not like ours. It was filled with quiet mystery and patient minds. They did not rush to be right. They lingered, letting patterns emerge. They began with gold, silver, copper, iron, and then, as their tools grew sharper, they found others hiding in ores and stones. Cobalt, nickel, zinc, each new discovery carried more than weight. It brought a question. Where did it belong? How did it behave? Did other elements echo its qualities? Answers drifted in, slowly, like dust swirling in a shaft of morning light. No one knew it yet, but they were assembling a pattern. The early charts attempted to catch it. Rows, classifications, speculative arrangements, ideas shared gently between minds, separated by distance and time. There was no internet, no global laboratory, only letters, books, drawings sent by hand. The quiet pace allowed something precious, a sense of wonder. As more elements were discovered, some began to notice similarities, tiny echoes between different materials that hadn't been obvious before. Some metals formed crystals alike, some burned or reacted in mirrored ways, all speaking faintly of something shared, something orderly. A map, just starting to reveal itself. We weren't ready for its full shape, not yet. But the edges were coming into view. The world was no longer a chaos of isolated materials. It was becoming a system. Bit by bit, the periodic table was rising. Slow, steady, almost shy. It did not announce itself. It waited to be seen. And when it was, everything changed. We are still in the quiet beginning. Let us rest here, a little longer, before the lines connect, before the pattern completes. Let it hover in the stillness. A chart not yet filled, a map not yet drawn, invisible, but promised. Close your eyes now. Let the idea float. We return soon. They gave them names, weighed them carefully, observed their reactions. Names like oxygen, carbon, sulfur floated into existence. But with each new discovery, a sense of chaos deepened. So many properties, so many behaviors, no clear path between them. Some elements seemed alike, others completely different. It was like collecting scattered pieces of an ancient puzzle, but with no picture on the box. Some chemists grouped elements by color or weight or behavior in flame. Others made long lists, memorized reactions, watched for patterns. A few noticed something. Every so often, properties seemed to repeat. Soft, shiny metals shared traits. Gases had their own families too. But it was all too loose, too fragile to build upon. The need for order remained. And into this quiet ache, a man named Dmitri Mendeleev appeared. Born in a far and wintry corner of Siberia, he came into chemistry with a deep curiosity and a mind shaped both by science and poetry. He believed the universe held hidden laws and that human minds were made to find them. In his studies, Mendeleev gathered every known element. He listed their atomic weights, watched how they combined with others, how they behaved under heat, in water, in air. He wrote notes on cards, one element per card. He shuffled them, sorted, rearranged. He spent weeks doing this. He did not believe the elements were random. He felt, with some deep inner certainty, that a structure was there. One night, caught in the still silence of study and sleeplessness, he drifted into dreams. In that dream, he saw the cards arranging themselves, laying down in rows and columns according to their properties. Each column, a family of elements with similar behavior. Each row increasing in weight and power. When he woke, he rushed to his desk. He wrote it down. The layout of the periodic table. Not just a chart, but a story. Spaces were left open for the elements yet unseen. He predicted their properties too, and years later, those elements were found and matched his descriptions. The dream, it turns out, was more than sleep. It was the mind, quietly arranging a universe. A quiet order hidden inside the wild facts. He called it the periodic system, and through it, matter itself began to make sense. From chaos came a kind of calm, a table of ideas, of families, of places where even the unknown had a home. This vision of order still lives today. We learn it in schoolrooms. We display it in labs. But once it lived in a single mind, floating first in thought, then in a dream, then on the page. Mendeleev leaned back in his chair. In the quiet laboratories of the 18th and early 19th centuries, a question hung in the air like mist over still water. What are the building blocks of matter, and how do they relate? Chemists, still alchemists in spirit, studied the elements one by one, the oil lamp beside him flickering gently, its soft glow falling across scattered notes, carefully written in a hand worn by thought. Before him lay a vision, not just a list, not simply numbers, but a shape, a pattern, waiting to be known. He had arranged the known elements by weight, gently sorting them from lightest to heaviest. But there was more than mere mass unfolding here. He looked at their properties, melting points, how they reacted with acids, the colors they took when exposed to flame. These tiny clues whispered deeper truths. And in the quiet of his study, he began to notice something. Patterns, repeatable, gentle arcs of similarity, stretching quietly across groups of elements. He began to place them, not in a straight line, but in something else. A table with rows and columns, each element a piece of some larger melody. Elements with similar properties fell into columns, stacking like memories, each one echoing the one above. But sometimes something curious occurred. One element would seem too heavy or too light for its given group. Rather than bend the rules or force the pattern to fit, Mendeleev did something quieter, more thoughtful. He left a space, a blank spot on the table, not as an error, but as an invitation. There was room, he believed, for discoveries yet to come. And not only did he leave spaces, he dared to imagine who those future guests might be. He predicted their properties, their behaviors, even weights not yet measured. Gallium, germanium, scandium, all silent at the time, yet already placed at his growing banquet. Among his peers, the reaction was cautious. Some found it bold, others strange, a little too dreamlike in its confidence. But as time passed, his predictions began to emerge from the lab, confirmed by the hands of chemists, astonished to find such detailed portraits already waiting for them. The table, once seen as a clever attempt, became something else entirely. It became a map. An orderly, balanced framework, not only of what was, but of what could be. A structure born from the patterns of nature herself, one that whispered the elegant design at the heart of matter, and suggested, gently, that the universe might love order after all. By the dawn of the 20th century, the periodic table had taken on a familiar shape. Rows and columns, patterned like a tapestry of chemical behavior. But behind its quiet symmetry, questions lingered in the spaces between the elements. Why did the elements seem to fall into groups, not just by mass, but by something deeper. Why did iodine, which had a heavier weight than tellurium, come before it in the sequence? The riddle would answer itself, not through weight, but through something more fundamental: the structure of the atom. Scientists had long suspected that atoms were more than indivisible spheres. Experiments with electricity and radiation hinted at pieces inside, but it was not until the rise of subatomic theory that the puzzle came into view. The proton, positively charged and dense at the atom's center, became the key. Each element had a unique number of protons, and this number, not the weight, determined its identity. This was the atomic number. Suddenly, everything clicked into place. The table's irregular bumps and misplacements smoothed into elegant order. Iodine, with 53 protons, belonged rightly after tellurium, which had only 52, even though iodine weighed a little more. The atomic number was the guiding thread, weaving through the tapestry of the elements. It was no longer just arrangement by weight and reactivity. Now it was arrangement by the very core of matter, the nucleus. This shift caused a deepening in how the table was seen. Not just a list, not even just a map, but a mirror of atomic reality. The table grew roots, anchoring itself in the very nature of atoms. Groups became families not only in behavior, but in inner structure. Columns, or groups, held atoms with similar arrangements of outer electrons, which explained why sodium and potassium, though different in mass, behaved so alike in water. This was not coincidence, but structure. Each row, or period, marked a new shell in the atom, another layer wrapped around the core. Lighter elements at the top had fewer shells, heavier ones more. From hydrogen to uranium, a quiet spiral unfolded across the table. Patterns once guessed became principles, determined by atomic design. This clarity did not come all at once. It grew gradually, as research deepened, but the vision it offered allowed the table to become more than useful. It became inevitable, like a natural law shaped in rows and columns. Scientists began seeing not just where elements fit, but where new ones would go. Empty spaces were no longer mysteries, but promises. The element with 43 protons, for example, technetium, was predicted to exist long before it was discovered in nature. Such precision only became possible through the atomic number. It gave order, but also potential. The periodic table was no longer only a record of chemistry. When we think of atoms, we often imagine tiny spheres spinning quietly in the dark. But inside those atoms, there is a structure, a careful choreography of electrons, moving within layers of invisible energy. These layers are called shells, or energy levels. Each shell can hold only a certain number of electrons, just enough to keep the atom balanced. Not too many, not too few. The first shell, closest to the nucleus, can hold up to 2 electrons. The second shell, a little farther out, holds up to 8. Then the third, and beyond, with more room as we move outward. As each atom adds more electrons, those electrons naturally settle into these shells, following a quiet rulebook of physics and energy. This is what we call electronic configuration. A gentle layering of electrons from the inside out. According to the energy they carry, low-energy electrons settle in close. High-energy ones float outward, like planets in expanding orbits. But what's fascinating is how this structure shapes the periodic table itself. Periods, the rows along the table, show us how many electron shells an atom has. Hydrogen and helium are in the first period, because their electrons only fill the first shell. Next come lithium, beryllium, and their neighbors. Their electrons fill the second shell, and so the second period is born. As we move left to right along a period, we're simply watching electrons find their place, one by one, inside the same shell, and when one shell fills completely, a new row begins. A new shell unfolds. This slow addition of electrons creates a repeating rhythm across the table, a pattern so subtle it can be easy to miss at first glance. But if you look closer, you'll see the dance. Elements in the same column share a shell structure, especially in their outermost layer. These vertical columns are called groups, and each one carries a family resemblance, not just in labels, but in behavior. Alkali metals, over on the far left, all have a single electron in their outer shell, which makes them eager to bond, to lose that one electron and become something new. To the far right, we find the noble gases with shells that are full, perfectly content. Rarely reacting between these extremes are rows and bands of elements, each guided by how electrons fill orbitals. These orbitals, smaller parts within each shell, come in different shapes, named S, P, D, and F. Each shape holds a maximum number of electrons, guiding how the shells fill up, beginning with the 1s, then 2s and 2p, then 3s and 3p, and so on. This progression is orderly, but not always linear. Sometimes electrons jump outward, skipping ahead because it costs less energy than staying close. This is where the beauty emerges, where chemistry whispers through physics and creates the living map of the table. What looks like a simple chart is really a 3D lattice of energy, each atom placed carefully, according to its internal orchestra, all dancing to the quiet rhythm of electrons, filling shells, following patterns, over and over. That repetition, that periodicity, is what gives the table its name. Moving across each period, we see the same outer shell filling slowly, and vertically, we see elements repeating in behavior. The halogens always near the end of a period. Always just one electron short of a full shell. Always reaching for one more. Group after group. Shell after shell. Row after row. It's a quiet architecture of decisions made by energy, of electrons settling into rest, balance, simplicity, elegance. That's the lattice of energy, gently holding everything in its place. And as you drift gently to sleep, imagine the atoms around you, settling too, their electrons resting, in soft nested shells, always drawn home by the quiet pull of energy, always finding their place on the lattice. Each element in the periodic table has a place that tells a quiet story, not just about its nature, but about its neighbors. It was a roadmap, made not from guesses or weights, but from the heart of matter itself. These vertical columns we call groups, or sometimes families, gather the elements who behave in much the same way. They are columns of kinship, connections drawn not by touch or sight, but by chemistry and quiet consistency. You see, elements in the same group often share similar reactions, not always identical, but enough to be recognizable, like echoes of each other. This is because of the number of electrons they carry in their outermost shell, their valence electrons. Just one small number makes all the difference. Let's start with group 1. The alkali metals, soft, silvery metals that never like to be alone. Lithium, sodium, potassium, rubidium, cesium, and francium, each with one valence electron, and oh, how eager they are to lose it. They react easily, sometimes even violently, especially with water. That's why they're stored away from air and moisture, hidden safely in oil. But in that restlessness, there's also a kind of warmth. Because those reactions, when guided gently, sparkle with light and color. Sodium, for example, gives off a warm yellow glow when excited. Potassium, a pale violet flame. Each element lighting its own quiet beacon. Now move one step over to group 2, the alkaline earth metals, softer personalities than their neighbors, but still reactive. Here we find beryllium, magnesium, calcium, strontium, barium, and radium. They have 2 valence electrons. It takes a bit more effort to coax them into reactions, but when they do, they form steady, stable bonds. Magnesium burns with a bright white flame, calcium, softly red-orange. Each one, a subtle gesture of its place in the world. Now, across the table, to the center block. The transition metals, groups 3 through 12, a land of strong, often shining characters. Iron, copper, gold, silver, not always grouped by strict valence numbers, but by their shared abilities. Complex, variable, but reliable in structure. They hold many of the sturdy materials we build our lives from. But let me take you now to the other side, to group 17, the halogens, fluorine, chlorine, bromine, iodine, astatine, and tennessine, each with 7 valence electrons, only one short of a full shell, which makes them hungry, eager, not aggressive, but keenly reactive. They bond easily, often with alkali metals, forming salts. Table salt, for instance, is just sodium and chlorine, joined in quiet harmony. Their reactions can be sharp, but always with purpose. And then, finally, we arrive at group 18, the noble gases. Helium, neon, argon, krypton, xenon, radon, and oganesson. With full outer shells, they are content. Still, unmoved, rarely reacting, they whisper of completeness. Neon lights up the night, a gentle red-orange glow in a glass tube. Argon fills the bulbs that light your room, silent and unseen. Helium lifts voices and balloons, floating gently above. The noble gases do not shout their presence. They simply are. Each group, each family, a quiet lineage written in electrons. Their behavior, their bonds, their reactions, all shaped by a shared structure, a soft map, hidden in rows and columns, drawing connections quietly across the table. These columns of kinship help us understand the gentle rhythm of the elements, how they hold hands with each other or pull away, how they light the sky or settle into calm stability. And in their stories, we see the patterns of the world, organized, predictable, and yet quietly wondrous. Just like the hush of night, settling softly over everything. Each row across the periodic table, known as a period, carries with it a quiet, unfolding tale. A tale of change, of gentle progression, and of balance found in the spaces between elements. When I glide my eyes across a row, from left to right, these are the alkali metals on the far left. Soft, silvery, eager to lend their electrons away. As we move rightward, step by quiet step, the elements begin to shift in personality and in purpose. First comes the transition away from pure metallic behavior toward elements that are still metal but not so reactive. I see more than just symbols and numbers. I see a story of transformation. The rows begin with metals, strong and reactive, their outer electrons held loosely, open to interaction. They become less willing to give up their electrons so quickly, holding them just a little tighter. This is no sharp border, just a slow evolution. The metallic luster softens, the tendencies shift, and by the time we approach the center of the row, we're near a crossroads between two worlds. Here we find metalloids, a special kind of element, poised between identities. They may conduct electricity like metals, yet behave chemically more like non-metals. The change is subtle, but steady. Now we reach the halogens, elements like fluorine and chlorine, reactive still, but with a different kind of fire. A desire to complete their own electron shells, to take what is missing, rather than offer what's already there. And at last, the noble gases. On the far right of the row, they stand apart, still, content. They are bridges, quiet connectors across the row. And then, we cross into the realm of the non-metals. With each step to the right, atoms cling tighter to their electrons, more reluctant to let go. They're more likely now to pull electrons in, rather than release their own. It's as though you're watching the sunrise of an idea, of how matter can change. Little by little, left to right, we move from metals that shine and share, through balance, seeking metalloids, to non-metals that hold and withhold. Each period is a chapter, each element, a word in, a language of structure and behavior. To study a row is to follow a calm, constant current of transformation, change without chaos, pace without pressure, like water shaping stone, slow, steady, deliberate, and always moving. Everything across these rows is part of a pattern, parts of a rhythm. The quiet drums of the universe beating beneath the surface, from one side to the other. The properties of elements change, their masses grow, their reactions evolve. They neither reach out nor push away, their shells perfectly filled, their balance already found. Across each period, the atomic number rises, the number of protons and electrons increasing with each step. But more than that, the way each atom behaves, shifts, softly. Listen closely, and you can hear the tale told across each period. A story not of isolated objects, but of relationships, placements, and becoming. Stars are more than lights in the dark. They are forges, silent, powerful, ancient, long before earth took shape, before water pooled, or winds stirred the surface of a world. There were stars. The first ones formed from clouds of hydrogen drifting together across the darkness, called together by gravity. Their hearts ignited under their own weight. Simple hydrogen, the lightest element, began to change. Inside the star, under immense heat and pressure, hydrogen fused into helium, a process known as nuclear fusion. This was the beginning of something vast, the first alchemy. Heat flowed outward, holding the star in balance. For millions of years, even billions, this dance continued, fusion creating light, warmth, and change. As the star aged, helium too would begin to fuse, becoming carbon, then oxygen, then neon, each new element heavier than the last. The larger the star, the longer and more complex its life. In the cores of massive stars, these reactions could build elements all the way to iron. But iron is different. It cannot be fused to release energy. When iron fills the core, the balancing act ends. The star collapses, its own gravity crushing inward. In mere moments, the core shrinks, temperatures surge, densities rise, and then an explosion, a supernova. In that instant, matter is torn apart, and reformed neutrons collide with atomic nuclei, forging elements heavier than iron, gold, uranium, platinum, each born in the heart of a dying star, scattered across space in waves of stellar debris. Over time, those raw materials drift again. Gathering in new clouds, new stars form, and around them, new worlds. That is how we came to be. Our Earth, made from stardust, our bodies, built of atoms born in stellar cores, calcium in our bones, carbon in the breath we exhale, iron flowing through every heartbeat, elements made not on Earth, but in long-dead stars. It is a quiet story, told not in words, but in matter. A slow unfolding across time, the periodic table, that collection of known elements, is more than a chart. It is a reflection of stellar history. Each element a marker, of heat, of pressure, of time, from hydrogen's light and first simplicity, to the heavy silence of lead and gold. The table is a memory of things once burning. So when I look at it, row by row, number by number, I see not just science, I see a whisper from stars I will never touch. The atoms within me, within you, each carries a story billions of years old. We do not create gold in our hands. We discover it within the earth, but its true birth was in fire and collapse. In the death cry of ancient suns, stars are not just above us, they are within us. Their patterns live among the pathways of our blood. So, as you rest, let this thought settle gently. You are made of stars. And stars are made of time. Sleep follows slowly, with that quiet in your heart, floating like dust through the corridors of the night sky, bits of carbon, oxygen, iron, and silicon carried through the cold dark, sometimes as isolated dust grains, sometimes as shimmering clouds of gas. Over time, the universe folded these remnants inward, gravity pulling particles together ever so gently. That is how Earth began, not as a world, but as a slow gathering of forgotten fragments. It is a journey, not of speed, but of subtlety. The periodic table does not shout with its rows, it whispers. The flames of ancient stars had long faded, their ashes drifting endlessly through the quiet arms of the galaxy. Tiny pieces, born from the hearts of dying suns, drawn into the quiet curve of a newborn solar system. They began to collide, not with fury, but with persistence. First dust, then pebbles, then rocks. The heat of their impacts stitched them together, layer upon layer, the core growing heavier, warmer. And then, one day, it was no longer dust and gas, but a sphere, still young, still molten, but becoming earth. Heavier metals, like iron and nickel, sank inwards. Lighter silicates rose, forming the first version of a crust. Though unstable and ever-changing, land began to hint at itself through that early chaos. The crust cracked and slipped, creating patterns that echoed tectonic plates. Were not yet what we know today, but tectonics had already begun. The constant movement beneath the surface pushed up mountains, opened basins, carved ridges below future oceans. The earth breathed through these shifts, even before there was air, and then, from the cooling silicate surface, certain elements began to form compounds that would later become familiar. Hydrogen and oxygen met one another in the right place at the right time, and water began to form. Not waterfalls or rivers yet, but clusters of molecules growing in number, again and again, over long spans. Comet impacts added more. These icy messengers crashed into Earth with gifts of frozen water. The temperature fell, the surface hardened just enough, and the rains began. Not the gentle rain we know, but warm, heavy, endless. It poured for ages, creating the first oceans. Water found the lowest places and filled them. This blue coverage, fitting the shape drawn by tectonics. And as the oceans formed, so did the beginnings of air. Volcanic vents released gases trapped within the molten mantle. Carbon dioxide, nitrogen, and a whisper of ammonia. Over time, lighter elements built what we now call the atmosphere. It was thick at first and toxic, but the foundation was there, and slowly, ever so slowly, the elements inside responded to gravity, rearranging themselves. The chemistry stabilized land, air, water, held in harmonious balance by the elements themselves. Calcium gave strength to emerging minerals. Silicon laced the rocks with structure. Carbon danced on the edge of life, and in the soil, enriched by volcanic ash and ancient sediment, new compounds waited. Potassium, phosphorus, magnesium traces. They waited for something alive to make use of them. But before life could begin, the earth had to finish this gentle work first, building a canvas, prepared by starfire, cooled by time, and painted by the quiet symmetry of the elements. Life, in all its quiet complexity, is built from only a handful of fundamental ingredients. Not dozens, not even 100, but just a few core elements that shape the body of every breathing creature and the structure of every growing leaf. Among the most vital are three names you've heard many times before: carbon, nitrogen, and oxygen. They drift in the air, cycle through the earth, and course through our own cells, endlessly, silently, as threads in the great fabric of life. Carbon is the artist. It draws the skeletons of molecules, the sturdy, flexible backbones of living chemistry. Carbon has a unique gift. It can form long chains, elegant rings, and intricate branching structures. This makes it the perfect builder, crafting the framework for sugars, proteins, fats, and DNA, the quiet libraries that hold the whisper of your being. Every breath you take, every sunrise plant you pass, holds carbon atoms within, working patiently, linking up with others, forming shapes seen and unseen. Nitrogen is the quiet worker of structure and rhythm. It binds itself to carbon, forming amino acids, the alphabet of proteins. Proteins are what life uses to move, stretch, defend, and think. Without nitrogen, the machinery of life would fall silent. Much of the nitrogen you rely on once floated far above in the calm night sky, making up most of the air overhead. But nitrogen gas is inert, calm, unreactive. It takes special processes, like the magic of legume roots and their bacterial helpers, to fix it into a usable form. Dropped into soil, passed up into shoots, wrapped into fluids. Nitrogen joins the circle and quietly vanishes back again. And then, there is oxygen. We think of oxygen as breath, and rightly so. It fills the lungs, feeds the blood, and fuels the slow burning of food inside every cell. Oxygen is reactive, always eager to bond, and this makes it a spark of energy in biology. It's not just in the air you breathe, but also in the water you drink, the glucose you make use of, and the rust on iron. Oxygen is everywhere. Life needs motion, and without it, things fall still. Together, these three elements form a triangle, a foundation upon which all life rests. They come together in thousands, millions of arrangements, creating textures, sparks, and forms. But why these, and not others? Nature's palette is not random. It is careful, intentional. The periodic table holds over 100 elements, but only a humble few are chosen again and again by life. Carbon for its versatility, nitrogen for its stability, oxygen for its energy. Others too in smaller amounts. Hydrogen is key, phosphorus, sulfur, iron. But it is carbon, nitrogen, and oxygen that do much of the shaping. In the quiet of a forest, these elements pass from soil to roots to stems and back again. In the stillness of your body, they move from breath to blood to memory. Atoms that were once in stars are now part of cells. And those cells feel the wind, carry thought, and give life to dreams. It is humbling and beautiful that from such simplicity arises all we see and all we are. When you lie down to rest and draw a slow, deep breath, remember the path of those tiny particles. How they danced through water, through leaves, perhaps even through the lungs of ancient creatures, before arriving here with you. Quietly, patiently, they wait to begin again. I want to sit with you and slowly explore the quiet strength of the transition metals. They shape the very foundation of our tools, our wires, even our bodies. Let's begin with iron. It is the heart of our earliest tools, the silent strength in the beams of buildings, the rails beneath. Trains. Though iron on its own is strong, it becomes something greater, something sturdier. When combined with elements like carbon, steel, born from that union, is the backbone of modern construction. We often take it for granted. The feel of a screwdriver in the hand, the smooth edge of a knife, the frame of a bicycle, all strengthened by iron, guided by its ancient resilience. And yet, as mighty as it is, iron is not without change. Touch it to water, mix in a bit of air, and it rusts. Softly, slowly, it reverts to a more natural state. Even strong things need care. Now, let's drift toward copper. This metal is warm to the eye, with a reddish glow, like slow burning embers. It hums quietly with something more. Conductivity. Copper carries energy, gracefully, from place to place. Electricity flows through copper wires, beneath city streets, through the walls, around us, into lamps and stoves, through screens and speakers. The energy moves, quietly, reliably, thanks to copper's open-hearted nature. It is soft enough to shape easily, but not weak. In plumbing, in architecture, even in coins, copper has been everywhere, and always, and within us too. Our bodies turn to copper, for its role in enzymes, for the balance of our blood, a metal outside and inside us, working in harmony with life. And then, there is titanium, a metal of poetic silence, silvery, with a strength that surprises. Titanium is remarkably light, and yet it endures wear. Others cannot. Resistant to corrosion, to fatigue, to time, used in aircraft, in bone implants, in gentle instruments for surgery. Titanium is the quiet companion of innovation. It does not loudly announce its presence, but where quiet strength is needed, it is there, forged in stars, cooled in earth, awakened by tools. These metals, iron, copper, titanium, each tells its own story. They are part of a greater family, called transition metals, part of the heart of the periodic table, with electrons ready to move. They bond with others, shift shapes, adapt. That's why we trust them. In machines, in medicine, in life, each one conducts, reacts, forms and heals. The modern world leans on them, quietly. And even long ago, before the digital hum of servers, before the burning lights of midnight cities, there was always metal, being shaped, guided, turned into something, lasting. This quiet trio, iron, copper, titanium, continues to stand beside us, supporting what we build and what we become. In the stillness of night, it's comforting to know that even the strongest things are calm, and even the most enduring can be quiet. The world we build rests gently on metals that do not demand attention. They simply hold steady, waiting. And I'll be here with more to explore when you're ready to return once more. The noble gases float at the far right side of the periodic table, quiet and still, from helium to xenon. Each one shares a signature. Trait, they do not like to mingle, not with other atoms, not even with each other. Their outer shells are full, complete, satisfied, and so they resist reaction. They drift through space and substance, almost untouched. Each breath a part of the great story, woven quietly into life. Iron, copper, titanium. These names may sound simple, perhaps even familiar. But like so many things in this quiet world, there is depth beneath the surface. Tonight, helium, small and light, rises above all else. It does not burn. It does not bind. Instead, it lifts, holding balloons high and voices higher still in moments of playful joy. In hospitals, helium becomes more than air. Bubbles of it cool, powerful magnets inside MRI machines, silencing the roar of technology with this whispering helper, unseen. Then comes neon, bright and aloof. It glows not from warmth, but from energy lightly passed through, a tracer of light inside glass tubes, drawing soft red signs along quiet urban streets. Neon does not burn itself out. It endures, flaring gently when invited, then fading into comfortable stillness again. Argon, the silent guardian, denser, a cushion between what must not touch, shielding light bulb filaments, filling the space with protection rather than pressure. When used in welding, it wraps the growing flame in calm, preventing oxygen from rushing in. Argon sees the world clearly, protecting without changing. Krypton and xenon, heavier still, more rare, more mysterious. Their names echo with hidden places, forgotten chambers. In lighting, xenon sparks a white-blue flash, briefly bright, then calm again, used in photography, in headlights, bringing clarity for just a moment, then letting twilight return. There is something deeply restful in their refusal to change. Inside the earth, they gather in pockets, unhurried, waiting. Their stillness is not emptiness, but patience. Their presence is not announced by scent or sound, only in the ways they allow things around them to glow, to float, to be preserved. Scientific minds once puzzled over their silence. Why did they not combine, not react? Now we know they are already at peace. Their atoms, spheres within spheres, rest in a perfect balance, noble in their stillness, not unfeeling, but complete. We use them to slow a process, to preserve a form, to carry out acts gently and without flame. And in this, they remind us that being moved by every force is not always a strength. Sometimes, the deepest power lies in stillness. These gases do not seek transformation. No urge to bond, no thirst to flare. They exist as they are, stable, self-contained, ancient echoes of stars, even in vast space. Noble gases wander unclaimed, gliding through the cold with quiet detachment. Sometimes, enduring without change, is the most graceful glow of all. The noble gases speak in silence, supporting, lifting, preserving, without ever needing to be noticed. There is something deeply calming in that kind of presence. Far beneath the familiar rows of the periodic table, there is a quieter realm. Two stretches of elements that sit apart from the main body, like footnotes written in a different hand. The lanthanides and the actinides. These are the elements of the F block, sometimes called the inner transition metals, although their role, like their location, remains a bit elusive. The lanthanides, beginning with lanthanum, are soft, silvery metals, used in powerful magnets, phosphorescent lights, and even telescope lenses. Their presence in modern technologies is gentle, but vital, like quiet gears ticking behind the face of a delicate clock. Then come the actinides, a weightier line, darker, both in mass and mystery. They are reactive, yes, but it's not their strength or shine that draws us in, it's their subtlety. Found nestled between barium and hafnium, They tend to behave in similar ways, almost reluctant to reveal their individual characters. And yet, each one has a story. Here, begin the elements like uranium and thorium, known for their radioactive natures and their possible uses in energy. Some occur naturally, but others had to be made, forged not in the hearts of stars like most elements, but in the minds and chambers of scientists. The first synthetic elements emerged in the early 20th century through processes of bombardment and decay, in labs that balanced precision and possibility, creating something new from what had never existed before. These were the transuranic elements, those that come after uranium, heavier and often fleeting. One by one they were discovered, or rather, created. Neptunium, plutonium, americium. Each name an echo of earthly knowledge and celestial wonder. Short-lived in many cases, their moments of existence were measured in seconds or less, like an idea, half-formed, slipping away almost as soon as it arrives. But their evanescence doesn't make them meaningless. In fact, it deepens the mystery. How far can we go? How many more blank spaces might still remain, just out of reach? Scientists often speak of the island of stabilities, a theoretical region beyond the current end of the periodic table, where superheavy elements might resist decay a little longer, long enough to study, perhaps even long enough to use. These elements may not exist yet, or, if they do, they remain elusive, waiting in the vastness of possibility where the known bends gently into the unknown. The search continues quietly, with teams around the world exploring new methods, new collisions, new nuclei, a patient science, a speculative one. That asks not only what elements can be, but how far the table stretches. Not just to complete it, but to understand its shape. In this corner of chemistry, discovery begins to blend with artistry, finding meaning in the margins, searching the shadows just beneath the surface. It is there, in those bottom rows and beyond, where the story of matter still unfolds, slowly and delicately, like watching ink drift through water. No rush, no certainty, just the quiet unfolding of the elemental world. Mendeleev never claimed to see the future, but in a quiet way, his table did exactly that. When Dmitri Mendeleev arranged the elements, lining them gently by increasing atomic weight and chemical likeness, something unusual happened. Patterns began to whisper between the columns, and in those gaps, those quiet, empty spaces, he didn't just leave room, he made predictions. He believed there were elements the world had yet to find, but the table already knew where they belonged. Eka silicon, Eka, aluminium, names made from Sanskrit meaning one beyond. These placeholders weren't fantasy. They had weight, tendencies, behaviors Mendeleev had never observed, yet he described them all the same. And when the real elements were unearthed, germanium, gallium, scandium, they matched his descriptions with gentle precision. This was the table's quiet gift. It was more than a map of what we had. It was a canvas for what we hadn't yet discovered. Again and again it hinted, then proved, that the universe followed, a kind of softness in its order, a natural alignment that waited to be recognized, not invented. Even now, long after new elements have stretched the boundaries of chemistry, the periodic table still carries that same quiet foresight. When scientists propose new super-heavy elements, ones that last only fractions of a second, their behavior is first imagined through the grid Mendeleev made. The table tells them how these ghostly atoms might decay, how they could react, and why they behave the way they do. It helps reveal properties without the need to always build first. It teaches just by sitting still. Not as a crystal ball, but more like a seasoned librarian, showing what fits where, based on years of rhythm and repetition. Today's periodic table is more complete, but not finished. There's still a stretch of unknowns out near the edge. Ununennium, unbenillium, names that are numbers only for now, but waiting for real, experimental souls. And when they come, they will slide easily into the pattern, because the table has already left a place for them. Even now, we use the same logic to learn about things we cannot see. Elements at the extremes of possibility, those added in high-energy labs, for moments too brief to touch. Physicists use the table's patterns to guess how these newcomers will interact, what they might bond with, what their electrons might favor. In a way, the table still whispers, as it always has, not just what is, but what will be, and what could be, if we patiently listen. The House of Law listens too, and gently unfolds the patterns that science holds in its memory, always calm, always ready for the next name to take its place. Somewhere in the pattern, there's always one more story, waiting to appear. In the quiet world of the arts, where brushstroke and silence meet, the elements of the earth have always held a guiding hand. Our senses, shaped by light, by resonance, and by the lines we trace in clay or stone, are deeply tied to the core materials of the natural world. Let's begin with color. From the lustrous red of cinnabar to the brilliant blues drawn from lapis and azurite, pigments have long threaded the beauty of metals into art. Cinnabar, a mercury sulfide, was crushed into a silky powder for the deepest crimson in ancient frescoes. Dangerous, perhaps, but unmistakably vivid. Copper, when mixed with acetic acid, gave birth to verdigris, that greenish-blue hue favored by medieval manuscript illustrators and by Renaissance painters for drapery and sky. Iron oxide, the simple rust of the earth, became one of humanity's first pigments. Ochres of red, of yellow, and burnt umber. Found in the caves of early humans, painted with careful fingers onto stone. Even lead, once ground into white lead pigment, became the base for so many classical portraits. Its opacity, its softness under brush, made the skin smooth on canvas. The way we see has always been shaped by what we could draw from the land. Now, let us gently shift from color to sound. Metals ring with a voice all their own. Bronze, struck into the shape of a bell or a gong, reveals its resonance through weight and tension. With every chime, you hear the alloy's inner harmony. Silver, delicate and bright, carries a clearer note, used not just in musical instruments, but in the very wiring of our listening devices, a quiet presence behind sound. Iron, strong and steady, forms the structural skeleton behind bronze drums and steel strings. Its vibrations, depending on tension and form, stretch across pianos, guitars, and even vast church bells. When we hear music, when we sense vibration, metal is behind the curtain. Woodwind instruments, timed percussion, brass horns twisted like sculpture, all rely on the element's response to stress and motion. A trumpet's flare, a cymbal's shimmer, a violin's silvery strings, each note is a conversation between the artist and the atom. And then there is shape. Stone, clay, glass, and metal form the building blocks of form and balance in sculpture and design. Marble, forged from limestone under pressure, responds to the sculptor's chisel like frozen silk. Michelangelo believed the statue already lived inside the block, his task merely to set it free. Bronze, once molten, is poured into every crevice of a mold. It captures not only the surface, but the gesture, the soul. Ancient Greek athletes, Roman emperors, shielded horses in mid-gallop, all held eternal in metal. Glass, made from sand and soda, becomes both fragile and strong under fire. In the hands of artisans, it is blown into translucent sculptures, window panes that tell stories through colored light. Copper and iron, zinc and tin, folded into architecture and jewelry alike, wrapping function in beauty. Even the humble terracotta, baked beneath the sun or in kiln, has spoken through centuries. From Mesopotamian tiles to Chinese burial figures, each shape we follow with our eyes, each texture we trace with our fingertips, began with elements pulled from earth and ash and ore. Pigment, tone, and form. They are not only the language of the artist, but of the planet itself. Elements are not passive. They are expressive, constantly offering us color, sound, and shape. And we simply learn to listen. If you hold a phone in your hand, you're carrying a map of the periodic table. Not all of it, of course, but far more than one might imagine. Each chip, each wire, each glowing surface is the careful blending of ancient elements into something that feels almost magical. Silicon is often at the center of it all. It comes from sand, but in its purified form, it becomes the lifeblood of the digital age. We etch pathways into wafers of silicon, layering delicate circuits, and coax from them the power to think, calculate, and connect. Without silicon, there would be no processors, no memory chips, no modern computing as we know it. But silicon alone is not enough. To bring a phone to life, to make it colorful and compact, patient and powerful, we call upon rarer things. Lanthanum, neodymium, praseodymium. The names may feel far away, but these rare earth elements have quietly become essential. Neodymium, for instance, helps shape the tiny magnets within your device, the kind that lets speakers sing. Praseodymium finds its place in colored glass and screens, shifting light ever so slightly to bring vibrancy to displays. And lanthanum, found in camera lenses, contributes to the delicate clarity we often take for granted when taking a picture. These rare earths are not especially rare in abundance, but extracting them comes with effort and care, and each is chosen for a specific gift, a quiet superpower, tuned to its role. A phone screen seems so simple, yet behind the glow, there's a subtle matrix of elements. Indium tin oxide is one form, enabling the smooth touch interfaces we rely on. Transparent yet conductive, solid yet delicate. Then there's lithium, an element that buzzes quietly through the veins of every battery. Light and reactive, Lithium dances with cobalt and graphite in carefully layered cells. Each battery is a tiny chamber of controlled movement, storing potential, releasing it in measured amounts whenever we call upon it. Cobalt brings stability. Manganese assists in energy management. Nickel adds capacity. All chosen not for their names, but for their balance, their harmony. Superconductors, though still in early stages for consumer devices, are another thread in this elemental story. With them, we glimpse a future where resistance fades away, where energy flows smooth and uninterrupted. In special labs, where temperatures drop low, we find elements like yttrium, barium, and copper, forming compounds that unlock this strange conductance. They show us that even now, there are powers within the periodic table yet to fully awaken. From smartphones to satellites, solar panels to sensors. It's as if the elements were waiting all along, not just in their natural forms, but in the combinations made possible when human curiosity meets patient experimentation. Modern society, in all its speed and connection, is built on the foundational blocks beneath our feet. The same atoms that once floated through stardust, now shaped and arranged to carry messages across oceans, to turn light into meaning, and voltage into thought. Each device, each machine, is a quiet ritual of arrangement. This is the digital alchemy of our time, not turning lead into gold, but whispering to the old elements and finding within them a way to build the future. Silicon from sand, lithium from salt, rare earths from stone, transformed not by spell or secret, but by science, by curiosity, and by care. The periodic table is many things: a chart of known elements, a guide to chemistry, a language of microscopic order. But tonight, let us think of it in a different way, as a quiet and patient calendar of the cosmos, because hidden within its simple rows and columns is a timeline, a story of when things became possible. From the beginning, the very beginning, there was only the lightest of elements, hydrogen and a little helium, and just trace whispers of lithium. These came about in the fireball of the Big Bang, not from stars or planets, but from the moment space and time could stretch and cool. As the universe expanded, it shifted into calm, and light elements held their places, simple and enduring. Then came the stars, great furnaces scattered across a darkening sky. Within their hearts, heavier elements were born: carbon, oxygen, nitrogen, forged under pressure and heat, layer by layer, cycle by cycle. Some stars lived and died quietly. Others, more massive, ended with elegant violence. Their ends were beginnings in their explosive final breaths. Elements like iron and nickel bloomed into being and spread across the void. The heavier elements, gold, uranium, plutonium, required even rarer conditions. Colliding neutron stars, or supernovae of remarkable force, tiny places in time, that gave us enduring matter. Look again at the periodic table. From top left to bottom right, it is not just a list, but a sequence, a layering of time. Each element, a page, a moment in the unfolding story of the universe. Hydrogen walked into existence first, then helium, then the rest, in time. Reading the table sideways is like reading the age of all things. Not by the years we know, but by the possibility of formation. What could not form in the early universe waited for stars to bring it forth. The heavier the element, the later it joined the story. This tale continues still, in stars yet unborn, in particles floating quietly in space, in the dust between galaxies, where tomorrow's matter may gather. We are built from the legacies of many kinds of stars, some calm, some rare, all of them keeping time in forms we now organize into a table. That humble grid is really a cosmic calendar, with its first days set in the deep past, and its later chapters still being written in the dark distances beyond. To look at it is not just to learn chemistry, but to glimpse time fossilized in elements. There is a moment, quiet and slow, when you stop trying to memorize the table, and instead you begin to see it. Not as a list of isolated facts, but as a landscape shaped by deeper things. A kind of map filled with rivers of relationships, hills that rise in regular intervals, and valleys where mysteries dwell. It's easy to learn the labels: hydrogen, helium, lithium, one after the other, like cities along a train line. But when you pause and let your focus soften, you might begin to feel something else. A hidden order, a kind of story. You start to notice why things sit where they do, why gases gather on one side and metals on another, why certain elements always seem to behave in familiar ways, and others surprise you. The table does not demand memory. It invites memory through meaning. Like how water naturally finds its way downhill, your thoughts will begin to flow when you trust the current beneath facts. Think of noble gases sitting quietly along the far right edge of the table, always composed, rarely reactive. Their full outer shells are like completed stories. Nothing needs to be added, nothing taken away. Now move your gaze to the leftmost edge, where hydrogen floats above a column of eager elements, the alkali metals. These are the ones who always want to give something away. Their single outer electron, easy to part with. Not because someone told you to remember it, but because the story of that one lonely electron makes its own quiet sense. You begin to wonder, why does potassium behave like sodium? Why does calcium sit just beneath magnesium? And you start to realize, it isn't coincidence. It's rhythm. The table sings a song of orbitals and shells, of balance and gaps, patterns passed along the rows, echoed throughout the columns. Every element is a character with a role, a temperament, a set of habits. Some love to give, others love to take, while a few stay elegantly uninvolved. The periodic table isn't merely data, it's a cast of quiet characters, arranged by laws older than any classroom. And once you start seeing the story, the facts become easier. Not because you worked harder, but because you listened longer. Somewhere along the journey, memory becomes understanding. And understanding becomes curiosity. The table, once a chore, becomes a kind of invitation. You begin to ask, what happens when these two elements meet? Why does neon glow and iron rust? You find that every cell on that chart is an opening line of a story not yet told. So when you next look at the table, take a deep breath, let your eyes wander, and let wonder lead the way. It sits quietly on the wall of many rooms. In classrooms, where children first learn about atoms, in laboratories lit with soft fluorescent light, in observatories where minds drift through the void of space, the periodic table, a simple grid of symbols and numbers, each square humming with quiet order, a map not of lands or oceans, but of everything. For all the cultures we come from, all the histories we carry, the periodic table remains a shared language. No matter the country, whether written in Cyrillic, Latin, or Mandarin scripts, the meaning is constant. Hydrogen, helium, carbon, gold. The names might sound different. The pronunciation may change, but the elements remain the same. It is a kind of alphabet of the universe, free from borders or belief, woven into the very materials we use every day, and the stars that shine above us. Every time we look through a microscope or aim a telescope toward the sky, we are drawn back to it, that gentle grid, silently reminding us that we are all looking at the same matter, governed by the same principles. Oxygen moves through the lungs of every person and into the leaves of trees around the world. Iron carries strength through pipes in Tokyo, New York, and Nairobi. Calcium builds the bones of a child in the Arctic, just as it does in the deserts of the Sahara. Different lives, one chart. In this quiet structure, there's no need to agree on politics or faith or borders, because every scientist, every student sees the same hydrogen at the top left, the noble gases along the edge, the lanthanides tucked away below. It is symmetry, not just of shape, but of understanding. A chemist in Prague, an engineer in Mumbai, a teacher in Buenos Aires. They all glance at the table and see familiarity. That is its gentlest strength. Universality without demand. Inclusiveness without force. It welcomes all who wish to learn and reveals itself slowly, in time. At first, it's a chart of weights and abbreviations. But with calm attention, it unfolds, element by element, valence by valence. Patterns emerge, rows known as periods, columns known as groups. Inside this quiet puzzle, electrons find their orbits, and the shape of every molecule begins to take form. It is not just chemistry. It is the arithmetic of stars, the geometry of life, the poetry of matter. Because in hydrogen, we hear the echo of the Big Bang. In carbon, the architecture of life. In uranium, the ancient memory of Earth's deep time. And in gold, a shimmer formed in violent stellar collisions, carried to us on meteoric winds, held now in rings around fingers, and dust in museum vaults. For all its quiet, the table is not still. Even the naming of new elements becomes an act of unity. Japanese scientists proposing nihonium, honoring their home, Russian and American labs working together to find oganesson, rivalries softened with shared purpose, discoveries folded into the table's shape. And so, the chart endures. It grows, slowly, respectfully. Names are proposed, tested, accepted, not just by one nation or group, but by a global community. IUPAC, the international union that guides its form, invites all corners of science to speak and listen, a quiet reflection of the cosmos and of ourselves. A place where differences transform into patterns, and patterns into understanding, floating between the microscopic and the cosmic, always returning to that grid. asleep or awake, whether we look through a lens or close our eyes beneath the stars. The periodic table remains there, patient, balanced, and whole. And so now, the table is almost still. Each element that once danced and glowed in our story has curled into rest. They are not gone, only quiet, as if the earth itself has taken a deep breath and slowly let it go. The periodic table, a map not just of matter, but of meaning, now sleeps beside us in memory. Hydrogen still flickers in distant stars. Carbon sighs in your breath. Iron rests in your blood, and gold lingers in your thoughts. Everything that is has come from somewhere older, something once forged in pressure, fire, or the spaces between time. The elements cradle us gently as night deepens. Above us, the sky is a silent equation. Stars twinkling with ancient chemicals, reshaping, unbreaking, becoming. Below us, the earth hums with oxygenated roots, magnesium-rich stone, and deep-flowing water. And here, in the quiet space between body and air, we drift with them. Your breath carries whispers of 1,000 thunderstorms. Your pulse echoes with calcium and potassium, steady and soft. Your body is not separate from the table. It is a page from it, curled now into a poem. And the table itself, the simple layout we explored through the hours, it does not command attention now. It hums. A humming, slow and tuning, not a sound but a sensation of things falling into place. One name leads to another, just as thoughts do. Helium, lithium, beryllium, sodium, calcium, zinc, each name a note, each atom a breath, a lullaby of molecules drifting outward into sleep. Maybe, just maybe, when you fall asleep tonight, you'll wander back to a time when these elements were stars, when they burned so brightly they forgot they would cool. And in that dream, you might sit by the table once more, tracing your fingers across oxygen and neon, letting your mind soften at the sight of copper and sulfur. The table is always there, in the quiet of the night, not to be studied now, only felt, not as science, but as story. And not as story, but as wind, soft, slow, steady. So let go of everything else now. Let the elements cradle your thoughts. Let the hydrogen in your cells tick gently toward the stars. Let the iron kiss in your red blood, lull you into warmth. You are made of this, sleeping in the arms of the very things you explored. This moment, this breath, is both you and the universe remembering itself through you. Rest now. The table hums ever so softly, and in that hum, may your dreams rise like vapor through the periodic skies.